Well, we know what they are. At least we know what the last 6 are, because they are a mirror image of this multiplied by -1 to the power of r.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's Pentagonal Number Theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me.
Euler's Pentagonal Number Theorem is really a 2-part statement, and it starts with Euler's observation that the product from k equals 1 to infinity of the quantity 1 minus q to the k, where this q remains unevaluated, expands out to give you the sequence 1 minus q
squared plus q to the 5th plus q to the 7th minus q to the 12th minus q to the 15th plus q to the 22 plus q to the 26 ...
And what he observed is that these numbers, where this is 1, this is corresponding to the empty set, k equals 0, starting with 1, and then going every other one, 5, 12, 22. These are the official pentagonal numbers, and by that we mean we start with one vertex, and that corresponds to 1, and then if we expand from that vertex into a pentagram, we add 1, 2, 3, 4 more, so for a total of 5. And so that's where we get 1 and then 5. And if we do it again, this time we're going to expand from the vertex and these 2 edges to draw a larger pentagram. And because each leg here has a point in the middle, we're going to want to repeat that on our larger pentagram, and also, of course, include the vertices, adding from 5,
6, 7, 8, 9, 10, 11,
12 to give us 12. And for good measure, we do it one more time. We have 2 points on each leg from our starter, so we got to add 2 points
on each of the new legs plus the new vertices,
and we go from 12 to 13,
14, 15, 16, 18, 19, 20, 21,
22, etc. All right, so the pentagonal numbers, these are part of the G-gonal numbers, so that if we went down to 4, this would be 5 pentagram, 5 pentagonal. Well, what about 4, which is the square numbers, essentially? So we would start with 1, and then we would add our square, and then we go to 4.
and then we expand our square and our leg dots and our vertice dots.
We go from 4 to 5,
6, 7, 8,
9, etc. on to 16. It's not hard to see. And of course, the 3-gonal, 1, 2, 3,
4, 5, 6, 7, 8, 9, 10.
1, 3,
6, 10, 15.
21. Very easy to compute because you're just taking 1 and adding 2,
And then add 3, add 4, add 5, and
add 6. And also, these are the binomial coefficients, and choose 2 for n greater than or equal to 2. Because 2, choose 2 is 1, 3, choose 2 is 3, 4, choose 2 is 6, etc., etc. Or simply the triangular numbers. These come in everywhere, but anyway, we're going to be talking about the pentagonals and other figurate numbers, or, well, I just said it, G-gonal, and sometimes folks will say figurate numbers, and there's a little bit of confusion or whatever, but it scarcely matters. It's just this is the background of where this pentagonal in Euler's pentagonal number theorem comes from, is because of this correspondence. From there, we can consider the 6 gonal numbers, which are the hexagonal numbers, and it's the same kind of thing, and on like that, and that would be the hexagonal numbers. So the thing about the G-gonal numbers is that they at least on the official ones, are always given by a quadratic. In the case of the pentagonal numbers, that quadratic is f of k equals 3k squared minus k over 2. And if we were to expand this out, we get at 0, we have 0. F of 0 is 0, f of 1 is 1, and f of negative 1 is 2. And you can just substitute in these numbers for k in here, and you'll find the same thing. And you will also observe that on the plus k side, plus k, let me make that clear, plus k side, then our numbers are going to match the pentagonals proper. 1,
5, 12, 22.
And as you might have guessed, the numbers that we didn't circle here,
2, 7, 15, 26.
and actually 0, are given here. 0,
2, 7, 15, 26.
dot, 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 in the k going toward negative infinity. K going toward plus infinity. And that's it. In fact, the reason that we even have a thing called the generalized pentagonal numbers is because of this. So we have, here are the pentagonals. And typically, I think there is a name for these by themselves, but typically we just think of adding the set of these values to this set to give us the generalized pentagonal numbers. And this generalized pentagonal numbers, this generalized is not the same generalization I refer to in the title card. So these are the generalized pentagonal numbers. Now I said that Euler's pentagonal number theorem is really a couple of statements that work together. This is the first statement and some basic background on what it is and what it's saying there, and why the relation to pentagonal numbers. So let's take a look at the second part of it. The second part, or the of Euler's pentagonal number theorem, is that the inverse of what we had, 1 over 1 minus q to the k. And what he discovered, or what he observed, is that for this statement here, this gives the sequence of a q series that looks like this. 1 plus q plus 2q squared plus
3q cubed plus 5q to the 4th.
Plus 22q to the 8th. So, what are these numbers? Well, obviously, this is just an index. The real numbers that are interesting are 1, 2, 3, 5, 7, 11, 15, 22, the coefficients. And these coefficients correspond to partitions of n. P of n is given by the sequence for n equals 0, 1, and then n equals 1, 1, n equals 2,
2, n equals 3, 3, n equals 4, 5, etc., etc.
77, 101, I'm pretty sure, etc., dot, dot, dot. So P of n are these numbers, and they are the number of partitions of n. And that's what it is. The function is just counting. So what are partitions? Well, for n, let's just do this. N is 0, 4, 5. A partition of n is a way that numbers less than or equal to n sum to n. In other words, 2 is a partition of 2 because 2 sums to 2, and 1 plus 1 is a partition of 2. Now there are no other ways to have any set of positive integers less than or equal to 2 that sum to 2, and that's it. So 3 is 2, 1, and 1, 1, 1. And for 4 we have 4, 3, 1, 2, 2, 2, 1, 1, 1, 1, 1, 1. All of these sum to 4. There are no other unique possibilities. And for 5, 5,
4, 1, 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, 1, 1, 1, 1, 1.
And for 1, it's just 1. And for n equals 0, it's actually 1, and that corresponds to the empty set. The values of P of n as n increases are given by 1,
And then 1, and then 2, and then 1, 2, 3, and then 1, 2, 3, 4,
4, 5, and then 1,
2, 3, 4, 5, 6.
7. Some conventions that are used are to say pi of I of n designates the actual partition. So P of n counts them, pi of I of n identifies them, where this I goes from 1 to P of n. Obviously, you have one partition for each of the number of partitions. So, for example, pi of 3 of n equals 4 is going to be the third partition of 4. So here's 4, 1, 2, 3. The third partition is 2, 2. Third partition, actually, don't even really need that, but 2, 2. And then, so further now that we have identified a partition, the ith, or the third, we can say that L of I, so this I always matches the I on pi, and we could put L of I of n, but typical, if it's not ambiguous, we can just leave that off. So we can say L of I equals the length or number of parts of pi of I of n. So the length L3 of 4 is going to be 1, 2 equals 2. There are 2 parts. And then further, the variable lambda indicates a part itself. So we're going to need a new index, j, or subscript here, where j equals 1 to li. So we have one part for each of the number of parts. And that's pretty much it. So pi of 5 of 5, let's say, is going to be 1, 2, 3, 4, 5. That's going to give us 2, 2, 1, with L of 5 equals 3, giving us lambda 1 equals 2, lambda 2 equals 2, and lambda 3 equals 1. And that's typically what you will find out there. Sometimes folks will use A, B, C, etc. for the parts when they're comparing and contrasting different types of partitions or partition sets, etc. And all of it is contingent on parts being listed in lexicographic order, which simply means that we're descending, I should say, non-increasing. So 3, 3. We can keep the 3, but we can't go to a 4. The 4 has to be above the 3 in the first place. It's helpful to see that you always start with one copy of n, and you always end with n copies of 1. And everything else is what you get running the gamut in between. So you could look at a grouping, all of those leading with 3, and the second column then is going to be non-increasing, etc. Easier to see with larger numbers, but if you get into this habit of writing these out, the way to do it comes to you very quickly, because all you're doing is you're looking to keep the order to the right also non-increasing, and so you're looking for the maximum number you can put in the leftmost slot, and then after you've done that, then you're going to look for the maximum number that you can put into the second column, etc.
Usually the right-hand side of the equation on a Q-series can be written as a summation of a term, but it is helpful to use sequences of numbers directly, so we can represent Q-series via a sequence representation and see what the numbers do. Okay, so all we're doing here is for each term of the product writing out the coefficients, but instead of the q's and an exponent, we're going to take the value of the exponent and just put a -1 at that location in the sequence. So where a -1 appears is indicative of the exponent.
So notice that the order is backwards. The 1 minus q squared factor is listed first, and then the 1 minus q sequence 1 minus 1. So if that happens, it's no big deal. It's going to be the same sum, obviously, but you have to be careful that you remember that the second placeholder is already taken. So we don't want to start here, so we have to start here on the third. 0, 1, 2, 3.
So at each step here, we're taking what is directly above, the sequence directly above, multiplying it by -1, and then copying it starting in the kth place, wherever we are. So at each stage we sum here, but we can also, once a leader of accurate terms has been established, then you can just do a truncated pyramid or triangle of the remaining of what the remaining things would be, which is going to be -1 times the same thing, just advancing 1 each time. So you see this finishing triangle and final sum to give us the sequence to so that all of the places are accurate as far as we decided to go.
That gives us a sequence where our non-zero values are occurring at k equals 0.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
12, 13, 14, and if we had added a column here, we would get -1 for k equals 15.
Okay, so just as we did with the product 1 minus q to the k, we can find the inverse by doing long division, which is what this is. starting with 1 followed by an infinite number of zeros. That sequence is our numerator, and our denominator is going to be the sequence given by 1 minus q to the k, as we saw before, with a plus or minus 1 whenever k is a pentagonal number. So that looks like this.
Whatever we have down here in this column is going to have to sum to 0, so that's got to be 1, and that's just a factor of that, so we're just copying this sequence, we're just moving it down, shifting it over 1. And same thing, except our factor is 2 here, because we get negative 2 to sum to 0, we need our 2. Multiplying this by 2, shifting it over, and adding it, etc. So that the inverse of this, the sequence given by it, is which is, of course, the partition numbers per Euler's Pentagonal number theorem. So something we can do, we can keep it finite by just considering the product to some r. And r is a number that represents our reach. As many factors as we want. The product of 1 minus q to the k, and we can do k equals 1 to r of 1 over 1 minus q to the k. Likewise, we might next add k equals 1 to r of 1 plus q to the k, and the product k equals 1 to r of the inverse 1 plus q to the k. Those are good starters. So for this one, we found that by multiplying out the factors, and k equals 5. And that's, of course, just simply one factor multiplied in, two factors multiplied in, 3, 4, 5. So it's easy to observe that the length of the interim sequence at any given step, the length of the partial product, a finite partial product expressed as this sequence, the only ones that are part of the infinite sequence are these first k plus 1 elements, because every sequence is beyond from there, and when it appears it changes the thing above. So the natural question to ask, what if r equals k equals 5? So when r equals 5, we have r plus 1 valid elements or sequence numbers. All the rest are not valid. They are subject to change. And we say that the length of this is 1, of this factor is 1, and it is the number 1. Then this has a length of 2, and this has a length of 3. So if I have 5 factors, I could take the empty set, plus 1,
plus 2, plus 3, plus 4, plus
5, and get
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
16. And what have I got? I got 1, 16. And of that 16, we got 6 that are valid. We have 10 that are not valid. Well, we know what they are. At least we know what the last 6 are, because they are a mirror image of this with multiplied by -1 to the power of r. Here, for example, our sign changes because r is odd. Otherwise, it would just be flat out symmetrical with sign and everything included. So we know more than just that these are wrong. They actually contain information. So we have already seen that this one here is represented by a sequence. I'm just going to count out the index, and when I hit a pentagonal number, then I'll write either a plus 1 or a minus 1. So 0,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11,
12, etc. for anyone wondering why we have a 0 place in our sequence representation when our product has k equals 1, essentially the answer is that the empty set is already included in the term. So this is the empty set to the power of r, which is the empty set. And we saw that the inverse of that is represented by the sequence 1, 1, 2, 3,
5, 7, 11, 15, 22,
30, ... So it becomes very natural to ask, given this one and this one as inverses of each other, what are those? We can do the same kind of thing, but our factors now are all positive, but they're still just two ones separated by an increasing number of zeros. And what we get,
1, 1, 1, 1.
got a problem. Symmetry is broken here. 5 2s. By this point, we know that these are the accurate numbers of the sequence. But there's more that we can do. Let's say this is our R, 0, 1,
2, 3, 4, 5, 6.
7. So R is 7. R equals 7, which means that these are k equals 6. And the k's are our partial product. It's just product up to k. And here, k equals r, which is as far as which was our reach. That's how far we reached. If we compute via multiplying these sequences up to r for the purpose of obtaining the rth number in the sequence, well, we didn't have to go that far because this is cyclic. It's every one. And so we can start, a cycle starts anywhere. So essentially what we're saying is that this is our cycle. 1, 1,
1, 2, 2, 3, 4.
5. We'll definitely be adding that and then totaling it. And then for that next one, then we will be adding
2, 2, 3.
4, etc. So we can just add all those up at once. We multiply these factors, we also keep track of this sum. We can do that at less computational expense than multiplying them out. So it's kind of a 2 for the price of 1 plus shipping and handling that we can, with this sequence, then extend, and we get 6,
8, 10, 12, 15, 18, 22, and
27. So the contention is that for this, for the price of 1, we get an additional r plus 1 accurate sequence elements. Or that is to say, by doing this to get the bonus at the end, we are essentially going to k equals 2r plus 1 for free. So we actually, if we really only wanted r, then we would only need half of the. So a natural question that arises when you do this is like, what is that sequence then? Well, observe that this total sum is this sequence here multiplied by the sequence 1, 1, 1, 1, 1, 1, 1. Well, 1, 1, 1, 1, 1 is really the sequence, is also the sequence of 1 over 1 minus 1. So that you end up with 1, negative 1, 1, negative 1, etc., etc. So, what we can do is start with the sequence that we are developing, which is 1, 1, 15, and let's just divide it by 1, negative 1. Here, in order to get a 1 up here, we're going to have to add 2 here. So we get a 2, negative 2. In order to get 1, we need to add 3, so we get a 3, negative 3. In order to get 2, we need to add 5. We need 19. And so, yeah, that's our sequence. Dot, 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 dot. So, as you can see, we can get our shipping and handling for free. We don't actually have to sum it as we go, but as we go, let's say we got to this point where that's 0, 1, 6, so that's r equals 5, and we multiply our 5 factors together to get this. At that point, all we have to do is divide what we have by 1, negative 1.
Okay, what I was trying to say badly here was that by skipping the k equals 1 term, and then so you're taking your product from k equals 2 to r, then you get the shipping and handling sequence. Then take a copy of that, multiply it by the k equals 1 term, and add the two sequences together, and boom.
To obtain 5 accurate elements of this sequence. So we can do much better, but only really because this cycle is the smallest it can be 1. If the cycle were 2 or 3 or what have you, the idea is that you're going to end up, you could probably, you might be able to do this step, but you're going to have something more complex here. That is beyond what I want to do for the time being. We're going to save that for another day, but there is a good research avenue here with possible speed-up algorithms for computations that currently do not take advantage of those speed-up opportunities. So let's move on from where we need to move on from, which is, at this stage, we need to first ask, what are these numbers? And is there a function corresponding to them? Okay, well, let's start by adding it to our card here. 1, 1,
1, 2, 2, 3, 4, 5, 6, 8, 10, 12,
15, dot, dot, dot. If we want to investigate this, this one right here, this sequence, let's take the inverse of that to get the sequence for this. So we just need we have I, so
1, negative 1, 0, negative 1, 1, negative 1, 1, negative 1, 2, negative 2, 2, negative 2,
and then 3, dot, dot, dot. In exploring what this might be, we take the inverse of this, and we obtained, for our fourth one here, this sequence. And still, we don't know what to call this yet. I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on. And that's it. Thank you very much for watching my video.